This question belongs to the topic theory of machines from the topic CAMs. This is little mathematics based. Here you are required to derive the displacement equation for the CAM. Okay, so a flat-faced follower is driven using circular eccentric cam rotating at a constant angular velocity omega. At the time t equal to 0, the vertical position of the follower is y of 0 equal to 0 and the system is in the configuration shown below. Okay, here is the flat-faced eccentric follower is given to you. So here the hinge is provided at this location. Okay, this is at the rest location when the follower is at the rest. Okay, so now let us say that the cam rotates in the clockwise direction. Let us say that the cam rotates in the clockwise direction. Now that this vector, let us say OB, this vector, let us say OB will be rotated by some angle. OB will be rotated by some angle theta, by some angle, okay, here by some angle theta, where theta is equals to omega t. Okay, and this is the position of OB after theta rotation, OB dash. Now this height, this displacement between B and B dash will be the displacement of the follower. This displacement, this vertical displacement of B dash, this vertical displacement from B to B dash will be the displacement of the follower. So now I can write OB is equals to E, and that is equals OB equal to OB dash equal to E, and let us name this point to be as some point C. Let us name this point to be as C. So I can write BC or equal to BC equal to, that is some displacement x, BC equal to some, okay, displacement of the follower is designated by y of t, designated by y of t or y, that is equal to BC equal to OB minus OC, OB is equals to E, and OC will be equal to cosine of OB dash. OC will be equal to OB dash cos theta, which is equal to E times of OB dash and OB are equal, so which is E times of cos theta, where E, if I pull it out common, so this will be 1 minus cos theta, or I can write this as 1 minus cos of omega t, which is matching with the option D. Okay, so this is the end of the answer. This question belongs to design of machine elements from the topic Spur Gears. Okay, and this is also a simple question. A spur gear with a 20-degree full depth teeth is transmitting 20 kilowatt at 200 radians per second. The pitch circle diameter of the gear is 100 mm. The magnitude of force applied on the gear in the radial direction is dash. Okay, so now power transmitted is 20 kilowatts at a speed of 200 radians per second. Okay, and here the pressure angle is given as 20 degree. Pressure angle is given as 20 degree, and the pitch circle diameter is 100 mm. So diameter D is equals to 100 mm, that is radius equal to 0.01 by 2, that is 0.05 meters. Okay. The magnitude of force applied in the radial direction. He is asking you to calculate what is Fr, that is. Okay, now coming to P is equals to tau into omega, that is T into omega, that is P is equals to 20,000 by omega, 20,000 by 200 is equal to 20,000 by 200 is equal to 100 newtons, 100 Newton meter of torque, 100 Newton meter of torque. Next, tangential force Ft is equals to torque by radius, that is 100 by 0.05, that is equal to 100 by 0.05, that is equal to 2000 newtons or 2 kilonewtons. Now on a gear tooth, if you see on a gear tooth, there will be a set of forces. There will be a normal force, that is say Fn, and there will be a tangential force, and there will be a tangential component of this force Ft, and there will be a radial component of this force Fr. So now the pressure angle will be the angle subtended between the normal force and the tangential force. So here Ft, if I relate these forces, that is tangential force and radial force, that is Ft is equals to Fr is equals to Ft times of tan phi, that is equal to 2 into tan 20 degrees, that will give me 0.73 kilonewtons of radial load, which is matching with option D. Is the end of the answer. This question belongs to the topic theory of machines from Gyroscope. Here is the question. The rotor of a turbojet engine of an aircraft has a mass of 180 kg and polar moment of inertia of 10 kg meter square about the rotor axis. The rotor rotates at a constant speed of 1100 radians per second in clockwise direction. When viewed from the front of the aircraft while flying at a speed of 800 kmph takes a turn with a radius of 1.5 kilometers to the left. Here the gyroscopic movement exerted by the rotor on the aircraft structure and the direction of motion of the nose when the aircraft turns r dash. Here the mass is given to you as 180 kgs and polar mass moment of inertia, that is given as 10 kg meter square, and velocity of spin, that is given as 1100 radian per second. Next will be the velocity, that is given as 800 kmph, and turning radius is given as 1500 meters. So omega of precision will be that is equal to V by R, that is equal to 800 into 5 by 18 divided by, this is for converting kilometers per hour to into meter per second, and this will be 1500. Okay, so now C is equals to I omega P. C is equals to I omega P, that is equal to 10 into 1100 into 800 into 5 by 18 divided by 1500. This answer will result in 1629.6 Newton meters of gyroscopic couple. So we have not yet decided whether it will be option A or option B, which gives the information about nose goes up and nose go down. So now let us decide the direction. Now here this is the aircraft. Okay, here is the aircraft. The propeller is rotating in the propeller is rotating in clockwise direction when viewed from the front. When you are viewing from the front, the propeller is rotating in clockwise direction, which means the vector is going away from you, away from the observer. As per the right hand screw rule, the fingers will be curling clockwise direction in the when the vector is pointed away from the observer. Okay, so now the second point is saying that the aircraft is turning towards left. The aircraft is turning towards left, which means that this is this aircraft about this axis, it is being turned to left. Okay, which means it is going inside the plane of the board. It is going inside the plane of the board. Now do one thing. Rotate this vector OX in the direction of this vector by 90 degree. Rotate OX in the direction of this vector. Okay, this vector or this turning the velocity of precision in the direction of omega p by 90 degrees. So if you rotate this in the direction of omega p by 90 degrees, this is rotating in clockwise direction. So okay, with respect to here, if you see, it is rotating in anti-clockwise direction. So here will be the vector, this will be OX dash, here it will be the OX dash. Now which will come out of the board, when you turn this vector, this will come out of the board. Now this vector will be representing active gyroscope. This vector will be representing active gyroscope. Okay, active gyroscope. Opposite to this vector will be representing reactive gyroscope. Opposite to this vector will be representing reactive gyroscope. Let us say this vector to be as x double dash. Now see, apply the right hand screw rule. As per this, if you see, the thumb is directed away and the front fingers are curling, so which means directly in the direction which the fingers are curling, as per this vector, the direction in which fingers are curling. So replace that vector here, replace this vector here. You will see that the nose will be dipping and the tail will be raising, which is matching with the option B. Okay, so this is the end of the answer. This question belongs to the topic theory of machines from mechanisms, analysis of mechanism. Now here is the question. In the 4-bar planar mechanism shown in figure, AB equal to 5 cm, AD equal to 4 cm and DC equal to 2 cm. In the configuration below, in the configuration shown, both AB and CD are perpendicular to AD, both AB and DC are perpendicular to AD, and the bar AB rotates with an angular velocity of 10 radian per second. The magnitude of angular velocity of bar DC is dash at this instant. Okay, so here is the given data. AB is given to you as 5 cm, AD is given to you as 4 cm, DC is 2 cm. Omega AB is 10 radians per second. Omega AB is 10 radian per second, and omega DC he is asking you to calculate. This is the configuration given for the 4-bar mechanism. Now let us just try to plot the instantaneous centers. This is 1, this is 2, this is 3, and this is link number 4. So now this will be instantaneous center number 1, I12. This will be instantaneous center I23, and this will be the instantaneous center I34, and this will be the instantaneous center I41. Now as per the Kennedy's theorem, if the 3 bodies are connected in such a way that they transmit relative motion, then their centros should lie on the straight line. So now if you see 1, 2 and 2, 4, 1, 2 and 2, 4 are fixed centers, 2, 3 and 3, 4 are called as moving centers. So now let us here the number of eye centers that is equal to n into n minus 1 by 2. So this is 4 into 4 minus 1 by 2, that is equal to 6. So here if you see, this will be 1, 2, 3 and 4. So far you have located 1, 2, 2, 3, 3, 4, 4, 1. Okay, now you are left with 1, 3, you are left with 1, 3. See here, when you are locating for 1, 3, it should be collinear with 1, 2 and 2, 3, 1, 2 and 2, 3, which means this line, 1, 2 and 2, 3, which means it has to be this line, somewhere on this line. Next will be 1, 4 and 3, 4, 1, 4 and 3, 4, 1, 4 and 3, 4. 1, 3 should be located at 1, 2 and 2, 3, this line. And similarly 1, 4 and 3, 4, intersection of these two lines. So these two lines are parallel, it will not intersect. So definitely I13 will be equal to infinite. I13 will be equal to infinite. Okay, so now coming to the another instantaneous center, that is 2, 4. 2, 4 should be collinear with 1, 2 and 1, 4, 1, 2 and 1, 4. This is the line here, 1, 2 and 1, 4. Here is the line. Next 2, 4 should be collinear with 2, 3 and 3, 4, 2, 3 and 3, 4. Here is the line. So this is 2, 4. Here is the 2, 4. Now remember here, if I13 is infinite, if I apply Kennedy's theorem, I12, I12, into omega 2 is equals to I12, 1323 omega 3, that is this value will be infinite. These two are finite values. Because of this, omega 3 will be 0 radians per second. If you have input link and output link parallel to each other, the velocity of the coupler link has to be 0. Omega 3 will be 0. Now coming to our discussion, here you are required to calculate the velocity of link CD. So now, applying the Kennedy's theorem, that is I12, 24 omega 2 is equals to I12, 24 omega 2 is equals to I14 or 41 omega 24 into omega 4. Okay, omega 2, this is omega 2 is the second link, that is AB, and this is link CD. So now this is forming a similar triangles. Whether I take the ratio of these two or ratio of this length to this length, or if I take the ratio of this length to this length, my answer will be the same. So here I can rewrite this as I13, 12 omega 2 is equals to I3414 omega 4, that is 1, 2, 2, 3. The length of 1, 2 and 2, 3, that is length of AB is given as 5 centimeter. Length of AB is given as 5 centimeters, and the length of and the omega 2 radian, the angular velocity is given as 10 radians per second. 3, 4 and 1, 4, that is link DC, that is 2 centimeter, that is equal to omega 4. So now upon solving this equation, now if you solve for omega 4, you will get this as 25 radians per second, which is matching with option A. Okay, this is the end of the answer. This question belongs to vibration, and from the topic free vibrations, and it is a very simple and basic question. The natural frequencies corresponding to spring mass system 1 and 2 are omega 1 and omega 2 respectively. The ratio of omega 1 is to omega 2 is dash. So here he is defining a first system. By connecting the springs in series combination of stiffness K Okay, this is the first system defined. So now we have the direct formula for this, that is equivalent stiffness, that is K equivalent will be equal to 1 by K1 plus 1 by K2. For this system it will be Ke will be equivalent to K by 2, and the natural frequency for this will be omega n is equals to root over Ke by m, that is equal to root over K by m, sorry, K by, it has to be 2m. This will be 1. This will be the natural frequency omega for system number 1. Omega for system number 1. Next, another system is formed by connecting the springs in parallel combination. So here the equivalent stiffness will be equal to K1 plus K2. This equivalent stiffness will be 2K. And omega 2 or omega for the system 2 will be equal to root over equivalent stiffness by mass, that is equal to root over 2K by m. So now taking the ratio of omega 1 by omega 2, that is equal to, here it will be K by root over K by 2m divided by root over 2K by m. So this will be in short equal to 1 by 2. Okay, this is the end. This is matching with option A. So this is the end of the answer. This question belongs to vibration, that is from the topic free vibrations. This is involving with conceptual depth also. So let us start our question. A uniform thin disk of mass 1 kg and radius 0.1 meters is kept on the surface as shown in figure. A spring of stiffness K1 equal to 400 Newton per meter is connected to the disk at the center A, and another spring of stiffness K2 equal to 100 Newton per meter is connected to the point B just above the point A on the circumference of the disk. Initially both the springs are unstretched. Assuming the pure rolling of disk for small disturbance from the equilibrium, the natural frequency of vibration of the system is dash radians per second. Okay, here the mass is given to you. Mass is given to you as 1 kg, and radius is given as 0.1 meters. Radius is 0.1 meters, and the stiffness of the K1 spring, that is stiffness K1 is given as 400 Newton per meter, and K2 is given as 100 Newton per meter. Okay, so and what else? Yes, that's all. And he's asking you to compute the natural frequency of this system, that is omega n. How many radians per second is asking you to calculate. So now this is the disk given to you. There is another spring attached. This is K1, this is K2. This is K1 and K2. Okay, so now here before identifying, first we need to write the equation of motion for a given system. This is point A and this is point B. The disk will be rotating about the instantaneous center. That instantaneous center will be lying at this point. So here this will be the about this point you have to write the equation of the motion for the given system. Now movements about I, instantaneous center I, if I write, that is equal to 0. So now let us say this disk is tending to rotate in clockwise direction. Let us say that this disk is rotate in clockwise direction. So now the inertial torque, that is restoring torque or inertial torque, will be acting in opposite direction of magnitude I theta double dot. This will be the restoring torque I theta double dot on the disc. Okay, and now once it is tending to rotate, in anti-clockwise direction, the spring K1 will be subjected to tension. So the force on A will be a tensile force which will be directed from A on the towards the left hand side, and next will be when the spring is tending to rotate in clockwise direction, that is spring K2 will be compressed. The spring K2 will be compressed. The force on point B will be compressive force. For compressive force you have to mark in this direction. Okay, now we have to mark in this direction. Now if you here the springs are located at different radii. Now if I analyze here, this spring will be having the displacement of x is equals to r times of theta. This spring will be having the displacement of x is equals to r time of theta, because this spring is located at a distance of r, radius r, and similarly for the spring which is on the circumference will have the displacement, let us say this to be as x1, let us say this displacement to be as x2. This distance will be x2 is equals to 2r times of theta. So first we need to identify, based on the location of the mechanical impedances, that is spring, these two springs, we need to identify based on these two springs. First write the displacements. Okay. Now here first term will be I theta double dot, that is restoring torque, I theta double dot. Next will be the spring force. Spring force will be stiffness K1 into this perpendicular distance. Okay, this distance, stiffness K1 into, it will be let us say that it is getting stretched. So here the stiffness K1 will be equal to K1 into r theta will be the spring force exerted. K1 into this will be the displacement in the spring, and with the stiffness, if you multiply, you'll get the spring force, and the perpendicular distance is r. And similarly for K2, if you write K2 into the distance for K2 from the instantaneous center, that is 2r into theta will be the spring force exerted on the spring which is present at the circumference, into perpendicular distance will be 2 times of r equal to 0. All the forces, if you analyze from here, the restoring torque, the spring force, and the spring force on the number K2 spring are acting in the same direction. Okay, so all the forces will be on the same directions. So now here I need to take it about the instantaneous center. I need to take about the instantaneous center, that is equal to mr square by 2 will be I will be mr square by 2, which is about the centroid, plus this distance, that is m into r square, that is equal to 3 by 2 times of mr square. Moment of inertia about point I, if I shift to this, it will be 3 by 2 times of mr square. So this will be 3 by 2 times of mr square into theta double dot. Okay, we'll write r in lowercase, 3 by 2 times of mr square, and next will be K1 into r square theta plus K2 into 4r square theta equal to 0. 4r square theta equal to 0. So now substituting all these values, that is 3 by 2 times of m is 1 kg. Radius is given to you as 0.1 meters, that is 0.1 square into theta double dot plus k is given as 400. R square will be cancelled here. I think here R square will be cancelled. Can cancel here R square instead of writing this term. 3 by 2 into 1. So R square will be cancelled. So 3 by 2 into 1, and this is K1 is 400. K1 is 400 and plus K2 is 100. 100 into 4, that is once again 400. So this will be equal to K1 plus K2 will be equal to 800, theta equal to 0. So in short, your equation will be this will be 1.5 times of theta double dot plus 800 times of theta equal to 0. So theta double dot is equals to 800 by 1.5 times of theta equal to 0. So this is of the general form. That is theta double dot plus omega n square, theta equal to 0. So omega n is equals to root over 800 by 1.5. So this many radians per second. So this will be approximately, omega n will be approximately 23.1 radian per seconds. Okay, this is the end of the answer.